This video has been produced for those students enrolled in the California Maritime Academy EPO 322 Diesel Engineering 2 Simulation course. This is Presentation 19, Main Engine Control Automation Architecture. Right, this is the Kongsberg faceplate for the bridge control. Some of the things that I want you to think about is on this faceplate, you'll see that that there are a slow down and a shutdown. Slow down are alarms that would cause the engine to reduce from C speed to a maneuvering speed. It's usually like full ahead if there was an alarm that was present. One of the things on this would be low pressure on the main engine lube oil, the camshaft lube oil, temperature high, main lube oil temperature high, main bearing temperature high. So anyway, those things that might be the problem be somewhat alleviated if the main engine was shut down or slowed down. On the shutdown, when you look at those underneath the button that says shutdown, you'll see this main lube oil pressure, camshaft lube oil pressure, thrust bearing temperature high, and overspeed. Now these are things that are serious enough that would warrant a main engine shut down to prevent damage to the main engine. So we're talking about you're out at sea, you're on bridge control. If the main engine lube oil pressure would suddenly drop below a certain threshold, the main engine would shut down automatically and would not restart until this had been cleared. So this is part of the architecture that would protect the engine in case of these problems. Below that, also under the fail, these are the things that are when the engine is starting, and these are some of the problems that you might have or be looking for. One of them down here, you'll see like the start too long. What that means is that the engine has not started, air has been applied, but it has not, the air has been applied for a longer period than necessary. Repeated start. It means that the main engine failed to start and the architecture is trying to start it again. Down below that, you'll see there's some load limits. A button named load limits and load limit override. The load limits is what's going on is you have a computer monitoring the main engine to prevent it from going into overload. Overload would be trying to run the engine at a very high rate of speed where you have poor weather and you're going against heavy winds, a heavy seaway. Your hull itself is fouled. Any of those could raise the amount of load on the engine. Now that's one of the things about diesels is that when they're brand new, the engine is sized so that it is oversized, I guess is usually the way that they're designed. And you don't have to run the main engine maxed out to be able to maintain your normal service speed. And the reason this is that over time, with hull deformations and with fouling of the hull, the load would go up on that engine to maintain your service speed. So these ships typically are designed so that the engine is sufficiently oversized that once under these fouled conditions, that the engine will be able to propel the ship at service. But specifically, when you get into a storm, when you have heavy winds, it is very common that you have to slow the main engine down. Now this used to be done manually by the engineers. They would be looking at their load indicator, which the load indicator is just you're looking at your rack setting. So the rack setting is how much fuel oil is being delivered into the engine from the high pressure pump. And you would be looking at your propeller speed. And there's a curve that you look at to be able to determine whether the engine is in overload or not. And then there was used to be a limiter on the main engine console, and you could dial down that limiter so that no matter where the bridge put their throttle, it would not go over that setting and would prevent the engine from being overloaded from the bridge. On this, you have an automatic program that it is looking at the torque being produced by the engine, and it will prevent the engine from going into overload. So it is always on, and it is always protecting the engine. Thermal load program, which is right beside it. Again, we're on the lower right-hand side. The thermal load program is this is a very big engine, typically around 2,000 metric tons. This particular one they're depicting on here is a 900 millimeter cylinder bore, so about 3-foot bore. These engines take time to heat up. So what happens is the thermal load program will slowly bring the engine up to full sea speed over a time period to prevent it from to allow it to warm up as you go. Typically, to go from full ahead up to full sea speed is usually somewhere around 45 minutes to an hour. Then beside that, you see a slow down pre-warning and a shutdown pre-warning, and underneath those would be overrides. The bridge can override any of these, though I can pretty much assure you in today's world that would be recorded, and if there was a problem with the engine further down the road, then that would be noted by the port engineers. Now on this is the main engine control system. The top plate is this right in here, as I've seen in bronze on quite a few different vessels for that War-Nor control. And what I want you to understand on this is these are usually LEDs, and it would tell you whether you're selected for bridge control or for engine control room, whether the handle has been moved to stop, whether the handle has been moved to an ahead position or in a stern position. Start blocked. That means that the main engine cannot be started, and pneumatically it's blocked from a start. Above reversing level. This is when you're trying to do a crash astern. The main engine typically can't be started in a stern if you're most vessels say about six knots through the water, right? If you're moving above 6 knots through the water, you'll not be able to go to a stern. The reason is you have a large propeller in the back of the vessel that water is moving across at 6 knots. That tends to keep the prop turning, and the main engine will be revolving. So to reverse this engine, you have to supply enough air to first stop the propeller and then get it to start moving in the reverse direction while it's being opposed by the water that's flowing across the flukes. This takes a lot of air, and it's called a crash astern. You can easily use up all of the air bottles and all of the air in the air bottles on one crash astern. So what this above reversing level is, if the main engine was turning higher than a certain RPM, it would prevent the engine from trying to start in a stern until that RPM had dropped down to a certain point. And this is because you would use all your air bottles and the engine would fail to start, and all you've done is now you've put in a 30-40 minute delay because you're going to have to wait for your bottles to fill again. Beside that is then you've got your cam in a head and a stern positions. This is very important with the Burmeister Wain. Again, each of the fuel links is switches from a head to a stern position by a pneumatic cylinder. Sometimes they hang up and don't shift. So what happens with the Burmeister Wain? When you go to start this engine, it's all right if you don't see in a head cam position or a stern. In other words, it doesn't match the direction you're going. That's okay until the engine starts to turn. But once the engine's turning over, you need to check this to make sure that the light comes on in the proper direction. Past that, slow turning. Slow turning is an option. It's not on all vessels, but that is to prevent, while you're testing the engine, while you're rolling the engine over, that you do not develop enough torque and enough force to push the ship along the dock and maybe break your lines. So a slow turning is just a smaller solenoid and allows less air to the engine to prevent the engine propeller from turning fast enough to be able to put a strain on your lines. Then the main start, underneath the start, that's the main start solenoid. When that opens, and then the engine is turned with full force. To the right of that, you see fuel off. The fuel off is your puncture valves. When that's lit, your puncture valves are activated and no fuel is being delivered to the engine. Below that is repeated start number 1 and 2. What's going on is the automation will roll this engine over when it's trying to start, and it's going to roll it over on air. Once the RPM comes up to a certain preset limit, then it is going to apply fuel by taking that pneumatic signal off your puncture valves, and then it shuts off the air to start air to the engine, and it waits so many seconds to see if the RPM has come up or if it's slowed down. If it's slowed down, the engine didn't fire. So what it does is it will go to a repeat start. So that's the second time. The repeated start number 1 is the second time this engine's tried to start. If it again fails, then it goes repeat start number 2. If it again fails from that, then it sounds an alarm on the bridge that the main engine has failed to start, and usually they're going to be calling down in the engine room to report that. All right, also on this page, again, you can see a list of your main engine shutdown. These are all the things that would shut the main engine down if an alarm occurred. Main engine slow down. Typically, again, that means that the engine will reduce speed from a C speed to usually full ahead maneuvering speeds. Some of the things about on startup that would cause the main engine, and also too, by the way, here we have the control air pressure, safety air pressure. Remember, control air pressure is your main control system, and you've got a pneumatic control system for this engine. Safety air pressure is a smaller bottle that is set up so that you have a secondary. When you hit emergency stop, what happens is that activates and sends an air signal to the puncture valves. So the safety air system is another supply to the puncture valves to make sure that you can take shut down fuel to this engine in emergency. All right, so on the load limiters, the other thing we talked a little bit just before on the load limitation, scavenging air limitation. It's looking at, when you're bringing this engine up, you're looking at whether you have enough scavenging air pressure to support the amount of fuel that you're injecting, and it's looking at the engine torque to see if you're in an overload. All right. Whenever you go on a ship, you're going to see a chart similar to this either in the control room or up in the engineering office, usually in the control room. What I want to point out to you is that you need to know, over on the right, here's your alarm points, whether it's going to cause a slowdown and what pressure or temperature, automatic stop. So let's take let's take jacket cooling water on the top. Inlet and outlet. Your normal is 3 bar to 4.5 bar at a temperature of at least a minimum, and you really want to be about, with the engine running, you're going to want to be more up around 80, but a minimum of 55. And the alarm will go off if you are below 3 bar and below actually this may be 65 degrees C, and the main engine will stop if you go below 2.5 bar. When you get on a ship, you want to know what your normal, especially for the main engine, what is normal pressures, what's abnormal, what will cause a slowdown, what will cause an automatic stop, because you're going to have to reset this engine, and you're going to be down there by yourselves. So you need to know what to look for if all of a sudden the main engine shut down while you're out at sea. It's very important, especially for the main engine, that you know your normal temperatures and pressures. The other one I typically talk to the students about is when you go down on watch, some quick indicators of if the engine is running well, is you look at your turbocharger speed, compare that, which is going to give you a good indication of engine load. Take a look at your exhaust temperatures, your scavenging air pressure, right? And typically, if it's on the larger engines, your load indicator, what's your rack setting. But the main one is turbocharger speed, scavenging air pressure, and your exhaust temps are very, very vital to give you just a quick indication of the health of the engine. So on all the new engines, you're going to see variable injection timing. There's a number of reasons for that, but one of the major ones when you're on heavy fuel oil is because the fuel properties will vary drastically, and your ignition delay will vary drastically. So literally, depending upon the fuel that you're burning, the point that it starts to burn can change enough that you have to retime that engine depending upon the fuel quality and its ignition delay. We've talked about that quite a bit over the course. But the other one too is that you understand that on startup, the Burmeister wane goes to full advance. And then once the engine starts, and that helps the startup, it gives you higher pressures, temperatures in the cylinder on start. Once the engine starts and the RPMs come up, then the timing is retarded back to its normal setting. Also, though, usually between about 40 and 80% power, they will progressively advance the timing to give you higher Pmax in the cylinder, which does improve fuel economy. But then once you get past 80% load, then it goes back to its normal settings. So the main thing on this, variable injection timing for heavy fuel oil ships, that allows you to adjust the timing of the engine depending on fuel quality to make sure that you get a clean burn and give you the best fuel economy. Now, variable exhaust valve closure you will also see in a lot of engines. Basically, when you have, and all the new engines are pretty heavily supercharged, and when I'm saying supercharging, it's what I'm really thinking of is turbochargers. You've got a lot of big turbos on them. You have a lot of valve overlap, or you're using a large portion of the air to cool the cylinder when you're at full load, right? So the exhaust valve will stay open past bottom dead center to allow that scavenging air to go through the ports and out the exhaust valve to cool the cylinder. Well, you can change this timing of this exhaust valve on the newer engines to allow you to, when you're running at low loads, to increase the compression, which increases the temperatures and the pressures in the cylinder to give you a better burn at low loads. So this chart, basically the main thing I just want to show you is and this one at about 45%, and this is advanced or before top dead center, right, up to 3 degrees. They're progressively bringing it up to about 3 degrees, and then they're going back to its normal setting up to 100%. What does that do? Max cylinder pressures. It's increasing the maximum cylinder pressures up to about 85% load, so that you, at 85% load, you have the same Pmax as 100%. That gives you a better fuel economy. And that's what they're showing here, specific fuel consumption. The amount of fuel that I burn drops dramatically down in that range, right? I'm burning less fuel, and most ships are running at about 85% load, so it'll save you money. All right. Now, on the exhaust valve, same type of thing that what we're showing on here is when you're taking at partial loads, by changing the exhaust valve timing, and that's what they're showing here on the lift. Basically what they're doing is they're going to increase the Pmax at partial load to give you a better burn. But once you're up at full load, that exhaust valve has to be open longer because you need to be able to cool the cylinder. On the big slow speeds, it's typically done by draining lube oil off of the power piston that drives the exhaust valve. So if you want to close the exhaust valve earlier, you just open up this control valve and allow that oil to drain down, and that will allow the valve to close at an earlier time. On the Kongsberg system, here is your puncture valve. This upper one is your variable injection timing, and it is a pneumatic signal. This is your rack to change, that's run by the governor, and it's typically mechanical. And this is the governor, what they're showing here is the governor output arm. Now, one of the things on, this is their depiction of this, and I'll show you in a second. There's this little pneumatic regulator, air regulator here, that controls the air going to all your different variable injection timing cylinders. And you can change it here. In real life, that upper rack, the bottom of the barrel is threaded, and we've talked about this before. So physically, when this pneumatic cylinder moves that rack, that cylinder will move physically up and down in the high pressure pump body, which changes the height of the spill ports, and that will change the timing. So your governor output, and this is out of Burmeister Wain, this is their drawings. When the governor output, when this changes, it will change through this lever arm, it will change, and that lever arm is pushing on the button on this regulator, will change your air signal to the pneumatic cylinders. The reason they do this is as this is moving, as this moves away, it's going to, or moves one direction or the other, it's going to push against this little button. And these stops here give you, is an adjustment to where it starts to adjust and where it ends its adjustment. So and it's kind of, this one's the best way to show it, but at low load, it's not hitting this pin. It is, the bar is hitting that pin, and there's a spring here pulling on it, right? And so your button is fully extended. But as this arm moves this way, right, from your governor, it's going to increasingly depress that button and change the air signal out. But once it hits that load pin, or that pin, as it keeps moving, then the pin causes the arm to shift the other direction, which then changes your air pressure, or your arm will output, and which is the outlet air pressure. So as it moves this way, as this button moves in, that is going to advance your timing to a maximum point, and then as it keeps moving, then very quickly it's going to go back to its original injection timing. So the thing that I want you to understand is that, and the main thing on this is that as you go into a storm, as the hull has a lot of growth on it, that will increase the resistance, and that engine, to get to a certain RPM, will have to develop, on the prop, will have to develop more torque, and will put more load on the engine. So frictional resistance increases fouling of the hull with sea growth, deformation, imperfections in the hull plates. You're hitting the dock, the tugs are pushing on you, all those dents on the hull. Do they slow you down? You bet. Fouling or imperfections in the propeller, and by the way, having sea growth on the propeller. There are services that will come out, and while the ship's in the water, will clean both the hull and the propeller for you. Wave resistance also will cause that, as you're going into a storm, it is going to cause the vessel to have the engine to increase in torque to maintain your service speed. What this one's about too, which is kind of interesting, is that with a certain hull shape, a lot of times just putting more power to it is not going to gain you what you think. Once you get up to a certain point, increasing the horsepower may only give you a small increase in speed. An example, it was on the old SL7s I started out on. They were 120,000 ship horsepower, and at full loaded on the main, and it had two main engines, 260,000 horsepower twin screw steam turbine. At 120,000 ship horsepower, you had 32 knots. Because of they burned, it was something between about 7 to 9 barrels per mile. When fuel got a little bit more expensive, they decided to slow down. They went to 60,000 horsepower instead of 120, and that got us 30 or 27 knots. So another 60,000 horsepower only got you 5 knot increase in speed. All right. So here's your propeller curve. And on the older engines, what's going to happen if you look, and this, by the way, is also, this is the Burmeister Wain. This is the one out of their book. But what they're talking about here is amount of engine power that you're producing. Typically, what you're going to be doing is looking at a rack setting. And on this is engine speed in a percentage. Now, number 6, propeller curve, light running for clean hull. So when you're right out of the shipyard, as you speed up, right? As you're increasing your rack setting, right? As I go up here, I'm increasing the amount of fuel I'm delivering. Your propeller RPM and the speed of the ship, by the way, is going to go up too. It's going to follow this curve up. All right. Now, number 7, power limits for continuous running. This is the maximum RPM on the engine, and they don't want you to, or excuse me, the maximum rack setting. Limit 4, torque speed limit, right in here. Now let's say I'm running at 95% of my rated horsepower, and I'm right in here. Okay, what I would do is I'm going to go down, and let's make it a little bit simpler and say that this is your load indicator. This is an indication of a percentage of what your high pressure fuel pump rack setting is. And again, this is RPM. So I'm referring to my load indicator, and I'm referring to my propeller RPM, and let's say I'm right up in here. Okay. Now, let's say we go into a storm, and actually let's pick 85%. So let's say I'm at 95 RPM and 85 on my rack. So I'm right about here. As you go into that storm, and there's more wind acting on the house, and there's more waves acting as the hull, to maintain that 85, the 95 RPM, what's going to happen is my rack's going to go up. And when I get up into this area, now I'm overloaded. So if I come down and I compare it the next time and I'm up here, I've got to slow down. So I'm going to slow down on the throttle. But as I do that, what I want you to understand, it's going to follow that curve down. So you may be going way, way, way down. Say, like, to get it down to here, you may have had to drop down to 65 RPM to make sure. So that's the propeller curve. It's used by engineers to determine the engine load, and so that you know when to slow down the engine when you're getting into heavy weather is typically where you use it. And this is the one right off the Sulzer, and you can see this operate on the simulator. That concludes this PowerPoint presentation. Thank you very much.